One type of differential equation that we can talk about here to solve, actually taking a differential equation and then finding the solutions, not being given the solutions, actually finding the solutions. One of those types that we can solve with what we're going to do is what are called separable differential equations. And the name is pretty nice because that's exactly what it means, is you can separate them. And here's what, one example, dy over dx equals 6x squared times cosine of y. And what the separable refers to is that we can separate the x's from the y's. I can get the x's on one side, constants up. Now, the x's on one side, the y's on the other. Now notice here, this differential equation, whatever I've chosen or we've started out anyway, I've got dy over dx. And that's important here. Instead of y prime, we're going to use the Leibniz notation dy over dx. Even if it, first of all, doesn't start with dy over dx, we're going to use dy over dx instead of y prime. Because that's what we're saying, we're going to want to separate the x's from the y's, meaning that not only the y's, but the dy's, and not only the x's, dx's as well. So I want to get the dy and the cosine y on this side, and then the x squared, 6x squared dx on the other side. If I can do that, if I get the x's on one side, the y's on the other, it's called separable. So yeah, can I do that? And what it amounts to is I'm going to be able to, separate dy over dx. I can multiply both sides by dx. And separate that dx from that dy. Then I can also do the same thing with the cosine y here, divide it. I'll do it in 2 steps here. Do it all in one whack if you see it there. Go ahead and divide cosine y, both sides. So I wind up with dy over cosine y equals 6x squared dx. I've separated the x's and the y's. And that's what a separable, you're able to do with a separable differential equation, okay? Separate the x's and y's. So this is a separable differential equation. You can't always do that, but those that you can, they're called separable differential equations. All right? And there is a nice little technique to solving those, which we will do on this next one. All right? So we're going to solve that one. Yeah, that one may be a little more fun than we want there. So let's solve this one. Dy over dx equals x squared over y squared. And so first of all, we know that one is separable. Pretty easy one to separate, isn't it? For one thing, we just cross multiply on that particular deal. Sometimes you can do that, all right? So we just cross multiply here. So that's our first step is in solving these separable ones is separate the x's and y's. Possible. And so we can, like I said, cross multiply, so y squared dy equals x squared dx. Pretty symmetrical there. So step 2 then, after you separate the x's and y's, step 2 will be to integrate both sides. So I'm going to integrate y squared dy, integrate x squared dx. Do the same thing both sides. That's usually a legal maneuver, and here's how this helps us. All right, so y squared, that's 1/3, like you just power rule, plus c, it is an indefinite. However, because the other side is also an indefinite, we're just going to choose, because we wind up getting the constants to the same side. So instead of doing all that every time, we'll just, on the x side, we'll just do the plus c part. So this side would be 1/3 x cubed plus c. Except it could be two different constants here, but we're going to get the constants on the other side, on one side together. So to save us that bit of work, because we'll have plenty of other work, as I'm sure you're probably aware. All right, so we'll put the plus c on that side. Okay? And so step 3, those solutions that we talked about on the first examples we did on differential equations, they were always y equals, we like the y equals function of x's. And so that's the third step, is solve, go ahead and solve for y. Get y on a side by itself. And that sometimes can be a fun part. I mean, the integrals can get fun too, but solving for y, this one's not too bad. What would you do? Multiply by 3, first of all. So I'm going to multiply everything by 3. So that makes it y cubed. 3 there, so the x cubed plus 3c. And talking real values here, so just the cube root both sides. Pretty good answer. Now, let me just show you this. What they'll do with this, all right, so 3 times c, 3 is a constant. 3 times c would also be a constant. What they'll do is they'll, instead, when we get things like that, some number times c, or c divided by a number, they'll just say, let's just call that a constant, because, I mean, we'd have to find, if you think back to those problems, we would plug in and find c, whether we find 3c or just, here's what I'm saying. What they'll do is they'll just call that 3c just one constant. And we'll call it k, just to make it a different one, but we could just call it c. But anyway, that's usually what they'll do, is they'll just make that be just a constant. All right, so there you go. This again is a family because it's x cubed plus any number. Plug in 5, 10, 100, negative, 1,000. Any of those would be solutions to this original differential equation. So, kind of interesting. All right, let's see another one. Y prime equals, so we're going to solve this differential equation. Y prime equals e to the x plus e to the x y squared. Y prime equals e to the x plus e to the x y squared. Now, some of them, like that one, are easier than others to tell they are separable. The question becomes, well, can I separate this, thus able to do it the way we were talking, the way we just did with that other example? This one may be a little more, well, first things first. Y prime, since we've got it, if we're going to do this separable way, the y prime, we need it as dy over dx. So let's first of all make that change. Probably different ways we can think of, but here's a way we can go ahead and separate this. Notice this one has a common factor of e to the x. So let's pull that off. And make it 1 plus y squared, parentheses there. Okay, we're on our way here. Yeah, I think we'll be able to separate that then now, can't we? Because you see it? What we're going to do? Divide by the 1 plus y squared. Multiply by the dx. We get this, right? See that? Divide by 1 plus y squared, so it'll be dy over 1 plus y squared because we're going to multiply by the dx. Both sides. Yeah, I didn't show what I did, but you see what I did there. Okay. Now what's next? Step 2? Yeah, so step 1 was a little longer than step 1 was over there. But that's the nature of the particular problem. All right, so step 2 now we're on, integrate both sides. Take the integral of both sides. And it looks like, well, they're both fairly easy. This one's probably the easier of the two. The integral of e to the x. That's just e to the x. And that x side, that's the side we put the plus c on. But this one also is not too bad, as long as you recognize it. What is that one? That's tan inverse, isn't it? Yeah. Some of them work out really nicely. Yeah, that's just it's 1 over 1 plus y squared dy, so that's tangent inverse y. Well, if we want to solve, go ahead and solve this out for y. Put y on the side by itself. Any thoughts? What if I do the tangent of both sides? What is this? Don't those cancel? Yeah, they're inverse operations, so they cancel one another out. Just get y. So yeah, just take the tangent of both sides. Easiest way to think of that. There you go. Y is the tangent of e to the x plus c. Okay? Question? Okay? All right. Let's see what else we can get ourselves into here. Solve y prime equals x squared y. It's easy enough, right? Again, for these separable ones, change it over to dy over dx. Y prime. And then think about separating them. Yeah, definitely multiply by dx both sides and then divide by y both sides. So dy over y equals x squared dx. Okay, so we've got something different on both sides again. Step 2. Integrate both sides. The right side's nice. This is just power rule, 1/3 x cubed plus c. What about left side? That's L and Y, isn't it? Oh. Okay. And it's absolute value Y. We'll talk about that. Also involve that discussion, what we do with that. Okay, so yeah, now we get into some different solving equation things. You got ln of y, ln of absolute value of y, equals 1/3 x cubed. Let's see. How do we solve this for y? How do we get rid of that ln? Kind of like we did here. Do the inverse operation, which that one's a little easier. What's the inverse operation of ln? E, yeah. E is the e to the power. We call it exponentiate both sides when I'm describing this to pre-calculus or whatever. Exponentiate both sides, but base e. In other words, do this. Make both of these sides be the power of e. Exponentiate both sides to e. Base e. See what I'm saying? Well, yeah, so these, just like the tangent inverse, they cancel one another. That will cancel out the e and the ln. And just get the absolute value of y equals e to 1/3 x cubed plus c. Now the deal on the absolute value, okay, so if you got the absolute value of x equals 3, x is either plus or minus 3. So this is y is either plus or minus e to 1/3 x cubed plus c. But we're going to do a little more with that. Here's how they get to the answer, because their answer would not look look nothing like that. Okay, so here, this stuff here, we kind of do the reverse of what we typically do, and that is split that up. You know, if we had, we did this earlier, e to the x is e to the 2x because we're adding, right? You add those. Well, here we've got them added, and so I'm going to split them up. So make that e to the y. And so e to the x plus y is e to the x times e to the y. So we're going this way, right? Instead of the other way, we usually go that way. We're going the other way. So e to the x plus y is e to the x, e to the y. So this is e to the 1/3 x cubed times e to the c. With me there? Okay. Still not the answer they would give you. Because e to the c, that's just another constant, isn't it? E to some power is just another number. That's just a constant itself. And so we could change that to k. And then not only that, but plus or minus, if I kind of group those two together, you got plus or minus a constant. That's still a constant. And so here's what the answers they would put. They kind of group all this stuff together as k, as one constant, because you're going to have a plus or minus either way. So anyway, just be aware. I mean, if you give me that answer, is it wrong? No. But just be aware that that's the way you can simplify it. Because all that's just a constant anyway. All right, that's what you can do on these anyway. All right, anything further on that? Good? All right. Try this one. All right, so let's solve y prime equals e to the x minus y. With initial value y0 equals 2. So probably I should phrase it a little bit more clearly. what they'll say is find the solution to y prime equals e to the x minus y with initial value y at 0 equals 2. That's my shorthand way of writing that. Yeah, so we're going to solve this, and then we're going to find the particular specific solution that works for that condition as well. Okay. All right. So we've only learned about separable, way to solve separable equation, differential equation. So it must be separable. So let's see if we can. Again, for separable, make sure you got dy over dx. Now this one, a couple ways you can see what we're going to do there, but I kind of need, first of all, to separate that. And with our previous discussion, you know, we can separate that as e to the x times e to the minus y. But even better than that, e to the minus y, that's 1 over e to the y. So this right-hand side, couldn't we just write it as e to the x over e to the y? Yeah. And that'll help by separating these out, right? Now all I have to do is cross multiply. E to the y dy equals e to the x dx. Well, that's going to work out rather nicely. Now we integrate both sides. That's e to the y, and that's e to the x plus c on this side. Okay, now this one's kind of the reverse of what we just did. I want to solve this for y, but it's an e to the y on this side. So what do I do there? Well, when I had the ln, I exponentiate both sides of base e. Here I have base e to y. Guess what I do? ln both sides, yeah. ln e to the y equals ln e to the x plus c. Because, yeah, the ln and the e will cancel, this will just be y. Now, you can't do that over here because you've got a plus still. That doesn't simplify as nicely, we'll just call it bx plus e. Which, that would have been where we finished last time, but with this initial value now, we can figure out what c is for this. We can actually figure out the particular c that we want because we have that initial condition. So what do we do there? What's the 0? That's the x, and the 2 is the y. So we've got 2 equals ln e to the 0 plus c. So that's 2 equals ln e to the 0 is 1. So I got 1 plus c in the parentheses there. 2 equals ln of 1 plus c. How do we solve that? Just like we did over there, right? E both sides, exponentiate both sides. So you got e squared equals e to the ln 1 plus c. E and the ln cancel, so we have e squared equals 1 plus c. So subtract 1, e squared minus 1 equals c. So the specific, particular solution that I want is y equals ln of e at the x plus c, but now I know c is e squared minus 1. So y, the answer is y equals ln e to the x plus e squared minus 1. Okay? Okay.